All right, welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are basically going to explore on one particular problem in advanced calculus, right? So basically, this is the problem, all right? We have been given this particular function, right? So if f of x and y is harmonic, right? Then we want to show that particular function f, now they have provided the coordinate of what? X, as x over x squared plus y squared, comma, the coordinate of y to be negative y over x squared plus y squared. We want to show that this particular function is also harmonic, right? And we want to know, or want to have enough details of our work very clearly presented, right? So before we can do this, it means you have to know some definitions. You have to know some terminologies, right? So we are going to begin with harmonic function, right? So solution. The first thing that we have to touch on is the definition of harmonic function, right? So that is going to be our step one. So step one, definition of harmonic function, right? So this is going to be the definition of harmonic function. So what does a harmonic function mean? So a function, right? A function, say f of x and y, is said to be harmonic if it satisfies the Laplace equation. If it satisfies the Laplace equation. So note the key word here, Laplace equation. So you can only call it harmonic function if it plays the role of satisfying the Laplace equation. Now, what does the Laplace equation do? The Laplace equation is basically focusing on second partial derivative of a function plus second partial derivative of another function. The result must be zero if you add these two partial derivatives. Right, so this is the Laplace equation. Die squared f with respect to die x squared plus die squared f with respect to die y squared, the result should be zero. So what it does is that, for instance, if you have f of x and y, when you take derivative of f, right, the second partial derivative of f with respect to x, and then you add it to the second partial derivative of f with respect to y, the result must give you zero. That is the Laplace equation. That is the Laplace equation. So basically, it deals with second partial derivative of a function, say x, in addition to a function, say y. The result must be zero. So that is all about the Laplace equation. Now, the second step that we have to know, so right now we have known the Laplace equation, right? So we have to show that, to show that u of x and y is harmonic, to show that u of x and y is harmonic, we must also prove that die squared u respect to die s squared plus die squared u respect to die y squared must be 0. So this must be 0. So for us to show that u of x and y is harmonic, we must prove that die squared u respect to die s squared plus die squared u respect to die y squared, the result must give us 0, right? So this is what we are representing as what? U, right? This is what we are representing as U. So we are representing the whole of this function as what? U. And you know that U is a function of X and Y. So that is what we have right here. So this is the main Laplace equation, all right? Okay, now we've understood this. The next step that we want to go on is the step 2, where we have to introduce new, variables to make our work very easy. You can see from here, right, as the first coordinate, right, the s coordinate of the function is a quotient, or it's a rational function. So we want to represent the whole of that function by a new variable called x. So step 2, introduce, or let's introduce new variables, right? Let's introduce new variables. So as I said here, we are going to say that let x, big X, equals the whole of this function. So x over x squared plus y squared. And then we also let big Y equals negative y over x squared plus y squared. Right. So we have let y represent the second term, and we have let big S represent the first term. Right. So that is the step 2. Now, we can now rewrite the function that we have as a function of x, u of a function of x and y, right? So thus, we can now rewrite the function, right? So the function as u of x and y equals a function. Now, remember, we have represented the whole of this as big S, and we have represented the whole of this as big Y. So we are writing that as f of big S, comma, y. You get it? So now we are not going to focus on this, because if you are to focus on this, the work will become very complex. That is why we represented f u of x and y to be equal to f of x, comma, y, capital S, comma, y. Remember, we have x and y here. So if you don't represent it as capital X and capital Y, it will be confusing, right? So from here, we are going to step 3. So with the step 3, that is where we are going to start with the differentiation, right? So step 3. So with step 3, we are going to start with the first partial derivative of x, right? So remember, this is x. We represented the first term as x, right? So we are going to differentiate the first term with respect to x, right? So derivative or let's call it first partial derivative of x, right? So that is step 3. First partial derivative of what? X. And you know that this is x. Capital X equals x over x squared plus what? Y squared. So we are going to take the first partial derivative of what? X. So you know that this, we are going to apply the quotient rule because we are having a rational function. Anytime you have a function over a function and you are dealing with differentiation, it's either you change it from the fraction to, a non-fraction function, right? So that you can use the product rule. If you want to maintain it as it is, then you are going to apply the quotient rule. So in here, we are going to apply the quotient rule, right? So you have to quickly recall your quotient rule techniques, right? Because I'm not going to show that process in here. I'm going to go straight forward. So if you have forgotten, check out the link below or at the description and then get more insight on the quotient and the product rule. Okay, so the x, capital X equals small x divided by x squared plus y squared. This here, we are going to find the first partial derivative of it. So you can see that we have in terms of x and what? Y. So we will find partial derivative with respect to x, and then we find partial derivative with respect to y as well. So we are going to start with differentiate with respect to x, right? So we are going to start with the x, right? So with the x, it means that we are going to have capital X subscript x, right? So we differentiate this with respect to x. So we have capital X sub x, and that is first partial derivative of what? X. And that will be equal to, so we are going to apply the quotient rule in here. And remember, the quotient rule says that you differentiate the first term, then you multiply it by the second term, minus you maintain the first term, differentiate the second term, right? Divided by the square of the second term. So we are going to have this 1 x squared plus y squared minus x into respect to x. So we're going to have 2x here divided by x squared plus y squared all squared. Right. So that is the differentiation with respect to x of x. Right? Differentiation with respect to x of x. So let's simplify that. So x with respect to x, so we have x squared plus y squared minus 2x squared divided by x squared plus y squared all squared, right? So we have this equals, we can see that we have x squared here and we have negative 2x squared. So naturally, this positive 1 will take one of this, right? So we are going to have y squared minus x squared divided by x squared plus y squared all squared. Okay? So the first partial derivative of x with respect to x is this. Now, we go again. Now, it is going to be first partial derivative of x with respect to y. First partial derivative of x with respect to y. So that is where we are going to have the x subscript y. The x subscript y. So that is differentiate or differentiating with respect to y. Okay, so differentiating with respect to y, it means that you're going to have x sub y, and that will be equal to 0 times x squared plus y squared minus x into bracket 2y divided by x squared plus y squared all squared, right? The reason why we have 0 here is that because we are differentiating with respect to y, and with respect to y, this will be constant, so we have 0 here. Then we maintain the denominator as we have here. Minus, we maintain this, then we differentiate this with respect to y. And you see that we have y here, so when we differentiate y squared, we're going to have 2y divided by the square of the denominator. And that is what we have right here. So this one all goes to 0, then we have minus 2xy divided by x squared plus y squared all squared. Great. So this is what we have for differentiating x with respect to y. Differentiating x with respect to y partially, right? That is, we are still on the first partial. So from here, we are going to step 4, right? So step 4, we are going to take the first partial derivative of y. So this is for the x. So when we took the x, as we have right here, we took the first partial derivative of x with respect to x. And then also we took the first partial derivative of x with respect to y. Now, we are coming to the first partial derivative of what? Y. In that instance as well, we will take the first partial derivative of y with respect to x. Then also we will take the first partial derivative of y with respect to y. So we are going to follow the same process. Then we are good to go. So we start with the x. So differentiating with respect to x, right? So differentiating with respect to x, so we are going to differentiate this with respect to x, okay? So we have y sub x, right? And that will be equal to differentiating this with respect to x means the numerator will go to 0. Then we maintain this. Minus, we maintain this, so it becomes plus. Then we differentiate this with respect to x, we have 2x. All right? Divided by x squared plus y squared all squared. So we have y sub x equals, this goes to 0, and then we have 2xy divided by x squared plus y squared all squared. Right. So that is the first partial derivative of y with respect to y. Now, we go to the second part, which is the first partial derivative of y with respect to y itself. So we have differentiating with respect to y. So we are going to consider this same function, then we differentiate with respect to y. So with respect to y, we have big Y sub small y equals, so with respect to y, it means that this is going to be -1 into bracket x squared plus y squared minus, we maintain this. So minus minus is going to be positive. We have plus y. Then we differentiate this with respect to y. So we have 2y. All divided by x squared plus y squared all squared. So we have y sub y equals -x squared minus y squared plus 2y squared divided by x squared plus y squared all squared, right? So this right here, we can see that we have positive 2y squared and we have negative y squared. So it will take one of the positive 2y. So we're going to have y squared. So we have y squared minus x squared divided by x squared plus y squared all squared. So this is what we have for the first partial derivative of y with respect to y. Great. So that is our step 4, right? So keep counting the steps. So we are going to go through about 11 steps. Then we are good to go, right? Then it will prove the harmonic function completely. Okay, so this is the end of step 4. Now, let's look at step 5. What step 5 have for us? So with step 5, we want to find the first partial derivative of u, right? Remember, we represented the whole of this function as u of a function of what? X and y. So we are going to start with the u, first partial derivative of u. All right, first partial derivative of u. So with that, we are going to start systematically as we did for the x and the y as well. With the first partial derivative of u, we are going to apply the chain rule, right? We are going to apply the chain rule. Since u of x and y is equal to f of x, y, f of big X, big Y. So we are going to apply chain rule. You know that chain rule is like a mother having a child inside her, right? So if you want to find what is happening to the child, you have to, go through the mom. So we call it, in mathematics, we call it chain rule. Right. So we are going to apply the chain rule since u of x and y is equal to f of big X, big Y. Right? So this is what we have. Isn't it so nice? So beautiful, right? So we're going to start with ux, right? Where we differentiate u partially with respect to x. And then we'll come to where we differentiate u partially with respect to y. Okay, so we are going to begin with the first partial derivative of u with respect to x, and then also we do with respect to y. So with respect to x, we have first partial derivative of the function f with respect to x, right? Partially respect to x times this, the one we did earlier, right? Plus first partial derivative of y times first partial derivative of what? X, right? So that is for the first partial derivative of what? X. So this is how the first partial derivative of u with respect to x will look like. We will expand this in the subsequent procedures. The second one is first partial derivative of the u with respect to y, and that is also equal to first partial derivative of the function itself times first partial derivative of the function x with respect to y, okay, plus first partial derivative of the function with respect to y times first partial derivative of the function y with respect to y. Okay, so that is basically what you need to know in this particular step 5. Now, with step 6, we are going to begin with the second partials, right? So in the step 6, we will proceed on this. We are going to build on this particular one. So with the step 6, we are going to take the second partial derivative of u, right? Second partial derivative of u with respect to x, right? Second partial derivative of u with respect to x. So, with respect to x, right? So, we are going to begin with that, and that is going to be u sub xx, right? Second partial derivative with respect to x. And that is equal to partial derivative. So, we are going to use the partial derivative symbol, right? So, partial derivative of the function f with respect to x times the first partial derivative of x with respect to x with respect to x, right? Plus first partial derivative of the function f with respect to y times first partial derivative of the function with respect to y with respect to x divided by with respect to what? X. So that is for the second partial derivative of u with respect to x. Okay, that is for the x, right? Now, what we are going to do is to expand the second term, right? So we will expand the first term and then we will expand the second term. So we will deal with them individually. So we take the first term, we expand, then we take the second term and expand as well. So you could realize that what we did right here is by taking this and then differentiating it the second time. So we begin with the first term where we have partial derivative of the function f with respect to x times the first partial derivative of x with respect to x or respect to x, right? So we are going to expand this, right? We are going to expand the first term, okay? So how are you going to expand this? Okay, so we are going to have f ss, right? We are differentiating this the second time, so it's going to be f ss times f. So we first dealt with this and we have f ss, right? The second one is going to be what? X x x, right? So this is going to be x the second time, all right? Plus, you know what? If you are differentiating a certain first partial derivative the second time, it means that is you're going to go through the mixed partials, right? So you go through the mixed partials within the second partial, right? So the next term is going to be f here, f respect to x partially, right? Now we are going to differentiate the same f with respect to y. Okay, so we differentiate this function. Now it is not going to be with respect to x again. It is going to be with respect to y. So fxy times yx times x, x, right? So we differentiated this with respect to x, and then the second time is what? With respect to y. Now, this is also going to be what? Yx, xs, yx, xx, right? You can decide to bring this first. It doesn't change the result. Okay. The next term from here is going to be fx, ss, right? fs, ss, right? So we are going to have the last term to be fs, x, x, right? So first of all, we took the first partial, right, with the second partial of this function, and we had this times this ss plus the mixed partial. So this is the mixed partial. So the mixed partial is either fxy times xyx ss, or you write it fsy times xxyx. So it's either you write this or you write this. So I chose to write the first one. They are all the same. They are all the same. All right. Now, we have been able to expand the first step, right? We have been able to expand the first term. So we can move on to the second term, of which it also entails the same idea, right? So we are going to use the same idea we used to expand the first term on the second term as well. So let's expand the second term. We follow the same procedure as we did for the first term. So expand the second term, right? Expand the second term. Okay, so we are going to carry this partial derivative of s of the function f respect to y times what? Respect to yx. So remember, we are still on the USS, right? So everything we are doing right here is respect to what? X. So this is going to give us fxy times, we have fy here. So we are differentiating with respect to what? X. So x comes first. Fx, then the y. Fx, then the y. Okay? Then this is going to be x, x, and then yx. Remember, we are differentiating with respect to what? X. Then plus fyy times fyx, fyx, right? So we are differentiating this, we are expanding this particular term, right? So the first term we expanded, we had this. Then you go again, you differentiate this. The second time you have what? Fyy. Differentiate this here, you're going to have what? Yx. Differentiate again, you're going to have what? Yx. Then the last term is going to be fy, y, x, x, right? So you differentiate this, right? You have that. You differentiate this with respect to x again. So you have y, x, x. So we have 1, 2, 3. So each of the expansion, you have 3 terms. 1, 2, 3. Okay? So that is the expansion of the second partial derivative of u with respect to what? X. So we have the first expansion and then we have the second expansion. Now, we can now combine the two expansions that we have done, right? So we can say that hence USS is equal to FSS into bracket XX all squared. We can see that we have FSS here, FSS, SSS, right? And then we also have another FSS, SSS, right? It's here. Yeah, it's right here. SS right here. So we just combine the two. right? We just combine the two, and then we have FSS x all squared, right? FSS x all squared. So that is the first step when you are combining, plus 2FSY xxyx plus FYY yx all squared plus fx xxx plus the last term is going to be the yy, okay? The last term is going to be the yy. So the last term, when you add it, the last term is going to be f y y y, right? F y y x x, okay? F y y x x. So that is the combination of this and this, right? So you can see that we have 6 terms in all, but this, for instance, this and these terms are common. So we combine those two terms, then we make the term very simple. So right here is the combination of the first term and the second term. All right. So that is the end of, step 6, right? Now we are going to step 7, where we are going to differentiate u again with respect to the second derivative of u with respect to what? Y. The one we just concluded is the derivative of u with respect to what? X. The second one, okay? So we are going to deal with u, second partial derivative of u with respect to what? Y. Second partial derivative of u with respect to y. So we go with the second partial derivative of u with respect to y. Okay? Second, that is step 7, right? Second partial derivative of u with respect to y. All right. So we are going to say that uyy is equal to partial derivative of the function with respect to x times respect to x respect to y plus partial derivative of the function with respect to y times y respect to y respect to y. Okay, so we are going to tackle it one after the other. So we expand this, then we expand this as well. So let's expand the first term. So expanding the first term, we are going to have partial derivative of f with respect to x times partial derivative of x with respect to y or respect to what? Y. Okay. So we begin with that journey as well. So we're going to have this right here. When you expand this, it means you are going to have FSS, right? FSS times XY plus FXY times YY times XY. So remember, we already did it from step 3 and 4, right? We did all this. X with respect to y, x with respect to y, y respect to y, and all that. We did it in step 3 and step 4, right? So we are not confused on this stuff. We already have this resource from step 3, right? So we are just expanding. Later we will bring out the actual, functions so that we can do the computations. Okay, so this is going to be plus fx x, y, y. Because we differentiate this, they differentiated again, this one again, with respect to what? Y. So we have y, y. Okay? So that is the expansion of the first term. So you can see that this one we have 1, 2, 3 terms, right? Now let's go to the expansion of the second term. Expanding the second term, right? So expanding the second term, where we have partial derivative of that respect to y, y respect to y. Okay, so this is what we are going to expand. This is the last expansion that we are going to have f x y, okay, times xy times y y, all right, plus f y y times y y y. The last term is going to be fy times y with respect to the second time of y. So when you expand this, right, you have this term, you have that term, you have this term. So you have the first expansion of the first term, and then we have the second expansion of the second term. So we are going to combine these two expansions. Then we can have the collective expansion for this second partial derivative of u with respect to y. So we can say that hence we have uyy to be equal to fxx of xy all squared plus 2fxy times xy times yy plus fyy times y sub y all squared, right? So this is a common term from here. So we can see that we have this here, and then we have same term appearing here, okay? So we combine that. This is appearing 2 times. So we square it, and then we bring it here. So xy, xy. So we bring it square. And then we can see that we have y, 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 y. And that is what is squared here. Okay? Then this one is the same as this. So we say that plus. Okay? We say that plus. Okay, so we add the 2 of that and we have plus. And then the last term is going to be those that are not having any common term. So we can see that this here and this here, they don't have any common term. So write them just as we can see. So plus fs xyy plus fy times y, y, y. Okay, so we can see that the combination of the first term and the second term is what is giving us this right here. Okay, is what is giving us this right here. Now, we have to add these two second partials to see if it is going to give us what? 0. Because that is our aim. For the function to be harmonic, it must satisfy the Laplace equation. And the Laplace equation, if you find the second partial derivative of a function with respect to what? X, and then you find the second partial derivative of a function with respect to y, the summation of these two items must give you what? 0. The result must produce what? 0. So let's try to add these two terms and see what it will give us. So we are going to sum these two terms. So that is going to be step 8, right? So adding adding USS and UYY, right? So we are going to add the USS that we had, the second partial of U with respect to X, and the second partial of U with respect to Y. We are going to sum these two, results and see what it is going to give us. So we are going to say that USS plus UYY is equal to FSS S into bracket X, right? Big XX all squared, okay? Plus XY, big XY all squared plus FYY into brackets YX all squared plus Y sub Y all squared, right? So we already know from the FUSS, we know the result we had, right? So, yeah, we know the result we had. So we can see that FSS was common, right? So we factored that out and then we use the big bracket, okay? We use the big bracket for it. So as you can see here, this is the big bracket, okay? So this right here is expanding to all the items in the bracket, right? It's expanding to all the brackets in the items in the brackets, right? So this is what we have for summation of what? The second partial derivative of U with respect to X and the second partial derivative of U with respect to what? Y. So this is what we are going to do. So from here, we can, okay, I think we left some of the terms from here. So some of the terms, the non-common ones that we cannot add it to the brackets are Fs, right? Fs of xxx plus xyy, close brackets, plus fy of yxx plus yyy. All right? Okay, so that is the summation of U and summation of U and what? Y. So summation of the second partial derivative of U with respect to X and the summation that of the second partial derivative of U with respect to Y. That is what we have right here. Now, what can we do? In step 9, we are going to try to evaluate each of the expression, right? Separately. So we are going to evaluate each expression separately. So that is what we are going to do in step 9. Okay? We are going to do that in step 9. So in step 9, evaluating each expression separately. All right, we are going to, okay, so that of x with respect to y is equal to, that of x with respect to y is equal to 4x squared y squared divided by x squared plus y squared all to the power 4, right? So remember, the x with respect to y, we had 2xy, right? We have 2xy. We had 2xy. So all divided by x squared plus y squared, all squared. So now, for us to square it, this is the result that we have, right? So this is the result that we have. Because we are handling this individually. So we handle this, 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 we handle this. Then we sum up to see if they will give us 0. Okay, so we go to the next term. We go to the next term. We go to the next term, of which that is x, right, all squared, right. So okay, so we have this right here, and then we have this right here. So let's sum the two and see something, right? So this and this will be equal to, so we're going to sum this and this, okay? So the summation of that is going to be x to the power 4, all right? X to the power 4 plus 2x squared y squared plus y to the power 4 divided by x squared plus y squared to the power 4, right? Because if you expand this, right, if you expand this, you have y to the power 4 minus 2x squared y squared plus x squared x to the power 4, right? And you know that minus 2x squared y squared will take off one of this. It will help reduce this one. So that is why we are having 2x squared here. 2x squared y squared. So we basically going to have x to the 4 plus y to the 4 all divided by the same denominator, right? They have the same denominator. So they have a common denominator, and that is what we have right there. Okay. So that is what we have for the summation of what? First partial derivative of what? The x with respect to x all squared plus first partial derivative of what? X with respect to y all squared. So what can we do? This term that we have right here, we can factorize it, right? So when we factorize this term, we are going to have x squared plus y squared all squared divided by x squared plus y squared to the power 4, right? So you can see that if you expand this, you get back to this, okay? When you expand this, you get back to this. So this is basically the same as this. So we did that so that we can reduce the denominator, right? So we can see that this will take 2 of this, right? So we're going to have 1 over x to the power 2 plus y to the power 2 all squared. Okay, so this is what we have for summation of xs all squared plus y xy all squared. Okay, that is what we have, right? Now let's proceed to the next step and see what we need to add up so that we can finish up the work. So we are going to do the next step, of which that is going to be, okay, so that of x with respect to y is equal to, that of x with respect to y is equal to 4x squared y squared divided by x squared plus y squared all to the power 4, right? So remember, the x with respect to y, we had 2xy, right? We have 2xy. We had 2xy. So all divided by x squared plus y squared, all squared. So now for us to square it, this is the result that we have, right? So this is the result that we have. Because we are handling this individually. So we handle this, 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 we handle this. Then we sum up to see if they will give us 0. Okay, so we go to the next term. We go to the next term. We go to the next term, of which that is x, right? All squared, right? So, okay, so we have this right here, and then we have this right here. So let's sum the two and see something, right? So this and this will be equal to, so we're going to sum this and this, okay? So the summation of that is going to be x to the power 4, all right? X to the power 4 plus 2x squared y squared plus y to the power 4 divided by x squared plus y squared to the power 4, right? Because if you expand this, right? If you expand this, you have y to the power 4 minus 2x squared y squared plus s squared x to the power 4, right? And you know that minus 2s squared y squared will take off one of this. It will help reduce this one. So that is why we are having 2s squared here. 2s squared y squared. So we basically going to have s to the 4 plus y to the 4 all divided by the same denominator, right? They have the same denominator. So they have a common denominator, and that is what we have right there. Okay. So that is what we have for the summation of what? First partial derivative of what? The x with respect to x all squared plus first partial derivative of what? X with respect to y all squared. So what can we do? This term that we have right here, we can factorize it, right? So when we factorize this term, we are going to have x squared plus y squared all squared divided by x squared plus y squared to the power 4, right? So you can see that if you expand this, you get back to this, okay? When you expand this, you get back to this. So this is basically the same as this. So we did that so that we can reduce the denominator, right? So you can see that this will take 2 of this, right? So you're going to have 1 over x to the power 2 plus y to the power 2 all squared. Okay, so this is what we have for summation of xs all squared plus y xy all squared. Okay, that is what we have, right? Now, let's proceed to the next step and see what we need to add up so that we can finish up the work. So, we are going to do the next step, of which that is going to go from the summation of the second partial derivative of u with respect to x, and then second partial derivative of y, u with respect to y. We saw the terms that we had, right? Now we have dealt with this, we have dealt with that, and we summed it, and we had this, right? Now, let's look at sx times yx plus x y times y y, and that result must give you 0. If you sum this and this, it must give you what? 0. Okay, now let's do that of xx, right? xxx plus y y y. That result must also give you 0. All right, so if you add this, okay, and you add this as well, it must give you 0. Now let's look at the last part of it, right? yxx plus yy. That result must also give you 0. Okay? So if we are saying that this is giving us 0, this is giving us 0, and this is also giving us 0, then it basically means that if we go to the step 10, where we are going to do the substitution into the summation, then it basically means that the result that we are looking for will be attained, right? That result will be attained, right? So let's try to look at that particular one and see if we are going to meet the Laplace equation or the demand of the Laplace equation. So we are going to look at step 10. In step 10, what we are going to do is to substitute the result that we are having right now into step 9, where we did the summation, right? The summation of the second partial of u with respect to x and the second partial of u with respect to y. So step 10, substitute the result, okay, into the sum that we did in step 9. Okay, we are going to do that substitution. So we know that we have USS plus UYY. That should be equal to 1 over x squared plus y squared all squared times fxx, right, plus fyy. Okay, now in step 11, what we are going to do to end the problem is, in step 11, we are going to use the harmonic function or the harmonic condition to, deal with this particular one. Since f is, harmonic, then it means that these two items that we have right here will go to 0. Right? And if this one is going to 0, then basically the whole of this thing is going to 0. Right? So we can say that in step 11, using the harmonic condition, we say that since f is harmonic, from the question, f is harmonic, okay? So if f is harmonic, then we can say that fss plus fyy should be equal to 0, right? So we are going to represent all of this to 0. So if that all is 0, then it means that uxs plus uyy will be equal to 1 over x squared plus y squared times 0, right? And you know that any argument over anything, 0 over any argument is what? 0. So we're going to have uxx plus uyy to be equal to 0 over x squared plus y squared all squared. And that is equal to what? 0. So this means that uxx plus uyy is basically equal to what? 0. So that is, we have basically proven the question, right? So they are saying that f is what? Harmonic. Now, if f is harmonic, then it means that fss plus fyy will be equal to what? 0, right? That means the second partial of the function with respect to x plus the second partial of the function with respect to y will be equal to 0. If that happens, then the whole of this goes to what? 0. Therefore, our conclusion will be equal to, therefore, our final conclusion will be equal to u of x and y will be equal to a function of x, comma, f of x over y, x squared plus y squared, comma, negative y divided by x squared plus y squared is indeed harmonic. All right? It's indeed harmonic. So, conclusively, we have boldly been able to conclude that this particular function that we have right here is indeed harmonic because it has been able to satisfy the Laplace equation, where we obtained the second partial derivative of the function with respect to x and the second partial of the derivative of the function with respect to y. The result, the summation of the result gave us 0. Wow, that is so beautiful and that is so interesting. I believe that this went well. Go back, rewatch, and you will understand. Thank you very much for watching. I really appreciate your time. Don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye bye.